Let us see composition of S.H.M. You know what is S.H.M? Simple harmonic motion, and you have defined linear simple harmonic motion. When the particle performs linear simple harmonic motion, that means it performs the oscillatory motion along the path AB. A and B are the extreme positions, O is the mean position, and while performing this oscillatory motion, the force acting on the particle, velocity of the particle, as well as acceleration of the particle changes at every instant. And this force acting on the particle or acceleration of the particle is always directed towards the mean position, and the magnitude of force and acceleration is proportional to displacement from the mean position. In this case, displacement is always measured from mean position. So this is about the simple harmonic motion. So whenever the particle is subjected to a simple harmonic motion, then it performs the oscillatory motions which satisfies the certain condition. Now, composition. What is the composition? Composition means combination. Combination of two S.H.M.s. Whenever a single particle is subjected to two or more simple harmonic motion at the same time or simultaneously, then what will be the motion of that particle which is subjected to different simple harmonic motions? Again, combination of S.H.M, we can say another word, superposition of S.H.M. And this word superposition oftenly occurs in sound as well as in light, because in sound we study the waves. In light we also study the waves, and whenever there is a wave phenomena, there is a principle which is called as the principle of superposition of waves in sound as well as in light, and we will study afterwards in the chapter sound as well as in light, that is principle of superposition of waves. Now, whenever mechanical waves travels through the medium, you know what are mechanical waves. Also, you are familiar with the waves. Waves are nothing but these are the oscillatory disturbance traveling through the medium without change of form. That means the energy passes from one point to another point in terms of oscillations, and that oscillatory disturbance travels through the medium. So whenever mechanical wave travels through the medium, either it is transverse waves or the longitudinal waves, then these waves oscillate every particle in its path. That means these particles performs the simple harmonic motion. Whenever a wave travels from one place to another place through the medium, then every particle in that medium performs the simple harmonic motion, and that's why these are also called as the simple harmonic progressive waves, because whenever these waves travels through the medium, these particles in the medium performs the simple harmonic motion. Okay, now what happens? One or more waves, two waves or three waves or four waves, number of waves are simultaneously passing through the medium. Then there is a possibility that These waves can arrive at a single point simultaneously. Let us we see. Suppose there is a particle here, any particle, and there is a one wave, mechanical wave, which travels through the medium, arrive at the point. Then this wave will oscillate that particle according to the characteristics of this wave. Characteristics means the amplitude and period of vibration. That means frequency. Amplitude and period of vibration. So this particle try to vibrate according to the characteristics of the first wave. Suppose along the same path there is another wave, say this wave, travels through the medium and arrive at the same point. This wave also try to vibrate this particle according to its characteristics. That means its amplitude as well as the period. Then what happens to that particle? These particles try to vibrate according to the characteristics of the second wave. This particle also vibrate according to the characteristics of the first wave. Then what is the resultant displacement of that particle? Suppose the first wave produces the displacement x1. Second wave produces the displacement x2. Then according to the principle of superposition of wave, the resultant displacement of that particle x is equal to x1 plus x2. That is the vector sum of the displacements produced due to the two waves. So whenever the single particle is subjected to two waves, each wave produces its own displacement at that point according to the characteristics of these waves. Then the resultant displacement at that particle is the vector sum of the displacement due to two waves. This is the principle of superposition of waves. Now what is the resultant displacement or resultant motion of that particle? So whenever a particle is subjected to two S.H.M.s, then what will the resultant displacement or resultant motion of that particle? If that motion is a simple harmonic motion, then what will be the resultant amplitude and resultant initial phase of the resultant simple harmonic motion? We have to study here. That means the composition of two simple harmonic motion. Now, in order to see the composition of two simple harmonic motion, we have to take a simple case. That means the period is same, also path is same. This is the condition. Composition of linear simple harmonic motions or two simple harmonic motions having the same period and same path. For that, you know that the general expression for the displacement of a particle performing linear simple harmonic motion, that is x is equal to a sin omega t plus phi. General expression for the displacement of the particle. There are two simple harmonic motions. Due to the first simple harmonic motion, suppose the displacement of the particle is x1. Its amplitude is a1 and initial phase is phi1. Amplitudes and initial phases are different, but the period is same. Period is same, that means the angular frequency is same. Angular frequency is same, that means omega is constant in both the simple harmonic motions. And path is same, that means the displacement is measured along the x-axis in both. This is the first simple harmonic motion, or the displacement of the particle due to the first simple harmonic motion. Displacement of the particle due to simple harmonic motion, that is second, x2 is equal to a2 sin omega t plus phi 2. Second. Displacement due to the first S.H.M., displacement due to the second S.H.M. Both S.H.M.s are along the same path, that means along the x-axis. Period is same, that means angular frequency is same here. But different amplitudes and different initial phases. A1 and A2 are the amplitudes and phi 1 and phi 2 are the initial phases of the two simple harmonic motion. Now, the resultant displacement of the particle according to principle of superposition of waves we have studied here now, x is equal to x1 plus x2. Resultant displacement due to first S.H.M., displacement due to second S.H.M., and the sum of these two displacement is the resultant displacement of the particle. We have to see what kind of the motion of the particle when it is subjected to two linear simple harmonic motion. X is equal to x1 plus x2, therefore x is equal to x1 is a1 sin omega t plus phi 1 and x2 is plus a2 sin omega t plus phi 2, x1 plus x2. Now we have to use the relation here, sin a plus b. I know sin a plus b, in mathematics you have studied, sin a plus b is sin a cos b plus cos a sin b. We have to use both the terms, so it is a1 into bracket sin omega t cos phi 1 plus cos omega t sin phi 1. This is the expansion of this term, plus a2 into again sin omega t plus phi 2, sin omega t plus phi 2, sin omega t cos phi 2 plus cos omega t sin phi 2. So sin omega t plus phi 2 is sin omega t cos phi 2 plus cos omega t plus sin phi 2. Therefore x is equal to, now we can separate the terms containing sin omega t here, sin omega t. So sin omega t into bracket, where are sin omega t? Here is one sin omega t, again here is sin omega t. So it is a1 cos phi 1, a1 cos phi 1. Another sin omega t is here, plus a2 cos phi 2 plus a2 cos phi 2 plus we can collect the terms containing cos omega t. Now look here, where are the terms where there is a cos omega t? Here is one term, cos omega t. So it is a1 sin phi 1, a1 sin phi 1. Another cos omega t is here, so it is plus a2 sin phi 2, a2 sin phi 2. Now we can consider as this a1 cos phi 1 plus A2 cos phi 2 as R cos delta. We can consider. And here A1 sin phi 1 plus A2 sin phi 2 as R sin delta. So this is 4 and 5. This bracket A1 cos phi 1 plus A2 cos phi 2 taken as R cos delta, and this bracket A1 sin phi 1 plus A2 sin phi 2 as taken as R sin delta. And we can use this in this relation. So what will happen? Look here, x is equal to A1 cos phi 1 plus A2 cos phi 2 is R cos delta. We can write R into sin omega t into cos delta plus here cos omega t into R sin delta. I can write this as R sin omega t, sorry, R cos omega t sin delta. R is common in this, sin omega t cos delta, cos omega t plus into sin delta. So I can write x is equal to R sin omega t plus delta. Now look at this relation. This is the resultant displacement of the particle, and R sin omega t plus delta. This relation number 1, relation number 2 and relation number 6. There is a similarity. What is similarity? x1, x2 are the displacement due to first and second S.H.M. X is also displacement. This is the resultant displacement due to two S.H.M.s. Here there is also sine term. In this also there is a sine term. In both the equation there is a omega, that is angular frequency. Here is also omega, angular frequency. There are phi 1 and phi 2 as the initial phases. Here delta is the resultant initial phase. So x is equal to R sin omega t is the same, is the similar equation as that of relation number 1 and 2. As relation number 1 and 2 represents the linear simple harmonic motion, we can say that the relation number 6 also represent the linear simple harmonic motion whose amplitude is R and initial phase is delta. So whenever, we can say that whenever the single particle is subjected to two simple harmonic motion, then the resultant motion is a simple harmonic motion whose amplitude is R, that is resultant amplitude is R, initial phase is delta, but this S.H.M. has the same period as that of the original simple harmonic motion. Okay, so whenever the particle is subjected to two simple harmonic motion, the resultant motion is also a simple harmonic motion whose amplitude is R and initial phase is delta. Now we have to find R and delta. First we find R. In order to find R, we have to use the relation number 4 and 5. Relation number 4 and 5. In order to find R, relation number 4 and 5. Squaring and adding the 4 and 5. What will you get? R square sin square delta. R square sin square delta plus here R square cos square delta is equal to R square into sin square delta plus cos square delta, and sin square delta plus cos square delta is equal to 1. So we can write R square is equal to r sin delta square plus r cos delta square. So r square is equal to r sin delta square plus r cos delta square. Now using the values of this r sin delta and r cos delta in this relation and doing some mathematical masala, we get r square is equal to a1 square plus a2 square plus 2a1 a2 cos phi 1 minus phi 2. But we want r, that is the resultant amplitude of S.H.M. So r is equal to square root of a1 square plus a2 square plus 2a1 a2 cos phi 1 minus phi 2. So this is the formula for the resultant amplitude of S.H.M. Now we have to find delta. In order to find delta, what we have to do? Again, we have to use the relation number 4 and 5. Here, we can take the ratio of these two. Divide relation number 5. Divide 5 by 4. What will get? R sin delta upon R cos delta is equal to A1 sin phi 1 plus A2 sin phi 2 upon A1 cos phi 1 plus A2 cos phi 2 and R sin delta upon R cos delta. It is a tan delta. So tan delta is equal to bracket A1 sin phi 1 plus A2 sin phi 2 upon here A1 cos phi 1 plus A2 cos phi 2 tan delta. And obviously delta is equal to tan inverse of A1 sin phi 1 plus A2 sin phi 2 upon A1 cos phi 1 plus A2 cos phi 2. So by using this formula, we can also determine the resultant initial phase delta. Now we have to see there is some cases, special cases, which depends upon the initial phase delta of the amplitude. So we say case first. That means if the two S.H.M.s we have seen, the phase difference between the two S.H.M.s is 0. That means two S.H.M.s having the same phase. That is phi 1 is equal to phi 2. Initial phase is same. That means phi 1 minus phi 2 is equal to 0. What it indicates, what it represents, if the two simple harmonic motions have the same phase. Suppose this is a circular path. In order to understand the phase here, this indicates that phi 1 is equal to phi 2. That means phi 1 minus phi 2 is equal to 0. That means the two simple harmonic motion or the particle starts the simple harmonic motion from the same place and moving in the same direction. Particle starts two S.H.M.s from the same place and moving in the same direction. That means phi1 is minus phi2 is equal to 0. And if phi1 minus phi2 is equal to 0, then cos phi1 minus phi2 is equal to cos 0 degree is equal to 1, and therefore the resultant amplitude R is equal to, what happens here? A1 square plus A2 square plus 2A1 A2, because cos phi1 minus phi2 is equal to 1, and this is equal to R is equal to square root of A1 plus A2 bracket square, that is equal to A1 plus A2. So if the particle starts S.H.M. from the same position and moving in the same direction because of the two S.H.M.s, then the resultant amplitude becomes A1 plus A2. There is the addition of amplitudes of the two S.H.M. And if the both amplitudes are same, if A1 is equal to A2, what happens? If A1 is equal to A2, then the resultant amplitude becomes A plus A, that is equal to 2A. This is the first case. That means if the particle performing simple harmonic motion, phase difference is 0. Second case, we will see here. In second case, suppose the two simple harmonic motions are out of phase. Out of phase, that means phase difference is pi radians, that is phi1 minus phi2 is equal to pi radian or 180 degree. What happens? Phase difference pi radians. Suppose one particle is performing simple harmonic motion in this direction. Due to first S.H.M., its projection will be here and moving in this direction. Another particle performing a simple harmonic circular motion in this direction. The angle between these two is 180 degree. In this case, projection is moving away from the mean position. So the particle starts the simple harmonic motion in opposite direction. If it is mean position, it has mean position if these are moving in opposite direction to each other. In such case, the phase difference is 180 degrees, and therefore cos of 180 degree is equal to -1, and therefore the resultant amplitude becomes R is equal to square root of A1 square plus A2 square plus 2A1 A2 into -1, that is minus 2A1 A2, and R is equal to square root of A1 minus A2 bracket square, that is R is equal to A1 minus A2. So when the phase difference between the two S.H.M.s is 180 degree, that means the particle is performing, single particle is performing a simple harmonic motion, both the simple harmonic motion in opposite direction, then the resultant amplitude is the difference between the individual amplitudes. And if A1 is equal to A2, what happens? If A1 is equal to A2, then R is equal to 0. The resultant amplitude will be 0 if both the S.H.M.s have the same amplitude. Third case, if phase difference phi1 minus phi2 is equal to pi by 2 radian or 90 degree. Pi by 2 radian or 90 degree. What it means? If this one S.H.M. starts from this position another S.H.M. starts from this position, then we can say that the phase difference between the two S.H.M.s is pi by 2 radian. That means the first particle is here, its projection is here, going away from the mean position. Second particle is here, it is going towards the mean position, and the phase difference between is 90 degree. So phase difference between the two S.H.M.s is pi by 2 radian or 90 degree. Then what is the resultant amplitude? Now cos phi 1 minus phi 2 is equal to cos 90 degree is equal to 0, you know, and therefore resultant amplitude R is equal to square root of A1 square plus A2 square plus 2A1 A2 into cos phi 1 minus phi 2, that is 0, and it into 0. So R is equal to square root of A1 square plus A2 square. This is the resultant amplitude if the phase difference between the two simple harmonic motion is phi. Again, if A1 is equal to A2 for the two simple harmonic motion, the amplitudes are same. A1 is equal to A2, then what is the resultant amplitude? R is equal to square root of A square plus A square is equal to square root of 2A square, and therefore R is equal to root 2 times A. If both the S.H.M.s have the same amplitude, that is A, then the resultant amplitude will be root 2A if the phase difference between the two simple harmonic motions is pi by 2 radian or 90 degree. I think you will understand all the part is mathematical. First, you should understand what is meant by a composition of a simple harmonic motion. We have taken here the example of two simple harmonic motion along the same path, having the same period but different amplitudes and different initial phases. And when the particle is subjected to these two S.H.M., then the resultant motion is also a simple harmonic motion whose resultant amplitude is R is equal to square root of A1 square plus A2 square plus 2A1 A2 cos phi 1 minus phi 2, and you have obtained formula for the initial phase delta, that is tan delta is equal to what? Tan delta is equal to A1 sin phi 1 plus A2 sin phi 2 upon A1 cos phi 1 plus A2 cos phi 2. Okay, I think you should understand that.